Welcome to G Fun Facts Online. Today, we are diving deep into a technology that sounds like science fiction, but is currently vibrating in the quiet corners of research laboratories at places like Oak Ridge National Laboratory and MIT. We are talking about a revolution that promises to upend centuries of thermal engineering. It challenges the oldest method humanity has ever used to dry things, which is heat. For thousands of years, the equation has been simple. Whether you are sun-drying fish in ancient Mesopotamia or throwing your jeans into an electric dryer in your basement, the process is the same. You add heat, you evaporate water, and you wait. It is a brute force approach. It is effective, sure, but it is incredibly energy inefficient. It destroys delicate materials, and it is slow. But a new paradigm is emerging. By harnessing the high-frequency mechanical power of sound, scientists are unlocking a process known as acoustic desiccation. This isn't drying by evaporation. This is drying by ejection. It is a physical rather than a thermal removal of water. By tuning ultrasonic vibrations to specific frequencies, we can now shake water molecules free from clothes, food, industrial sludges, and even the air itself. We are going to explore the deep science, the groundbreaking applications, and the future potential of harvesting water with ultrasonic vibrations. To understand how sound can dry a pair of jeans or pull drinking water from a desert breeze, we have to start with the physics. We need to understand the fundamental interaction between acoustic waves and liquid water. Traditional drying faces an immense thermodynamic hurdle known as the latent heat of vaporization. To turn just 1 kilogram of liquid water into vapor, you have to inject approximately 2,260 kilojoules of energy. This is an immutable law of physics. It explains why your clothes dryer is likely the second most energy-hungry appliance in your home, right after your refrigerator and HVAC system. You are paying for the energy required to phase change water from liquid to gas. Acoustic desiccation bypasses this phase change entirely. Instead of heating water molecules until they fly apart as steam, ultrasonic technology uses mechanical force to atomize them. At the core of this technology is the piezoelectric transducer. These are materials, often ceramics like lead zirconate titanate, that have a unique electromechanical property. When you squeeze them, they generate an electric charge. But conversely, and this is crucial for our purpose, when you apply an electric voltage to them, they change shape. If you apply a high-frequency alternating current to a piezoelectric transducer, it expands and contracts thousands of times per second. In ultrasonic drying applications, these transducers vibrate at frequencies typically between 20,000 cycles per second and 1 megahertz. So what happens when you apply these vibrations to something wet? When these high-frequency vibrations are applied to a wet, porous material, like a cotton shirt or a sponge, the energy is transferred to the water trapped inside. This happens through a fascinating three-step mechanism. First, as the transducer vibrates, it creates capillary waves on the surface of the water droplets. As the intensity of the vibration increases, these waves become unstable. Second, we get cavitation. The rapid oscillation creates alternating high and low pressure cycles within the liquid. During the low pressure cycle, vacuum bubbles form. When these bubbles collapse during the high pressure cycle, they release intense localized energy. Finally, we get ejection. The combination of unstable surface waves and cavitation creates a phenomenon called atomization. The water is physically torn apart into microscopic droplets, creating a cold mist, and is ejected from the fabric or material. Because the water remains in liquid form as a mist, rather than turning into vapor, the process does not require the massive energy input of latent heat. It is akin to shaking a wet rug, but on a microscopic, ultrasonic level. Now, let us look at the most relatable application of this technology, which is the laundry revolution. Researchers at the U.S. Department of Energy's Oak Ridge National Laboratory, led by Dr. Ayub Momin, pioneered the direct contact ultrasonic fabric dryer. Their prototype does not look like a traditional tumbling box. Instead, it resembles a press. When wet fabric is pulled across the piezoelectric transducers, the water is atomized instantly. In demonstrations, a sodden strip of fabric enters the mechanism and exits dry and cool to the touch mere seconds later. The water is converted into a cool fog that is simply sucked away by a fan and collected in a tank. The advantages here are staggering. First, there is speed. While a thermal dryer might take 50 minutes to dry a load of laundry, ultrasonic technology can theoretically do it in less than 20 minutes. Second, and perhaps most importantly, is energy efficiency. Because it avoids the latent heat of evaporation, the system is up to 5 times more energy efficient than resistive electric dryers. If widely adopted, this could save billions of dollars in residential energy costs annually. And third, there is fabric preservation. Heat is the enemy of clothing. It shrinks fibers, fades dyes, and creates lint, which is essentially pieces of your clothes breaking off. Ultrasonic drying is a cold process. Your favorite black jeans would not fade, and your wool sweaters would not shrink. But let's move beyond laundry. While drying clothes is about convenience, the application of acoustic desiccation to atmospheric water harvesting is about survival. Harvesting water from the air in arid environments often involves materials called sorbents, like metal organic frameworks or hydrogels. These materials act like super sponges, sucking moisture out of the air even at low humidity. The problem, however, is getting the water out of the sponge. Traditional systems collect water at night when it is cool, but then have to wait for the heat of the day to evaporate the water out of the sorbent to condense it. This cycle is slow and limits water production to once per day. In late 2025, a team at MIT unveiled a game-changing approach. They discovered that specific ultrasonic frequencies could break the weak molecular bonds, specifically the van der Waals forces, holding water molecules to the sorbent material. By attaching small ultrasonic actuators to the water harvesting plates, they could essentially shake the water out. Thermal desorption takes hours, but ultrasonic desorption takes minutes. Because the release is so fast, the system does not have to wait for a day-night cycle. It can absorb, shake, and release water dozens of times a day, exponentially increasing the water yield of a single device. The MIT team found this method to be significantly more efficient than thermal heating, making it viable for off-grid applications powered by small solar panels or batteries. This acoustic water tap could revolutionize water access in desert regions. Another sector where this is making waves is the food industry. Traditional drying, or dehydration, often ruins food. High heat destroys vitamins, alters flavor profiles, and changes the texture of fruits and vegetables into something tough or rubbery. When ultrasound is applied to plant tissue, like an apple slice or a grape, it induces a rapid series of compressions and expansions, known as the sponge effect. The acoustic stress creates microscopic channels within the cellular structure of the fruit. These channels provide an expressway for moisture to escape to the surface, where it can be easily removed. A particularly powerful technique is ultrasound-assisted osmotic dehydration. Here, fruit is placed in a sugar or salt solution while being blasted with ultrasound. The sound waves break down the boundary layers that usually slow down the process, allowing water to leave the fruit cells much faster. The result is dried fruit that retains its bright color, most of its vitamin C, and a texture that is closer to fresh fruit than the leathery standard of thermal drying. Beyond the home and kitchen, acoustic desiccation is poised to solve heavy industrial challenges, particularly in sludge dewatering. Wastewater treatment plants produce massive amounts of sludge, a semi-solid slurry that is expensive to transport and dispose of because it is mostly water. Removing this water is difficult because it is bound tightly to the solid particles. High-power ultrasonics can disrupt the bacterial cells in the sludge, releasing the bound water that mechanical pressing cannot reach. This reduces the volume of waste significantly. In pharmaceutical manufacturing, heat is often a liability. Many drugs are heat-sensitive and degrade if dried thermally. Ultrasonic spray drying allows for the creation of precise, microscopic drug particles at low temperatures, ensuring high potency and better solubility in the body. So, if this technology is so superior, why isn't it in our homes yet? There are a few challenges. First is cost. Piezoelectric transducers are currently more expensive to manufacture than simple heating coils. Second is coupling. Sound waves do not travel well through air, which is why the clothes dryer requires direct contact with the drum. Engineering reliable contact mechanisms for tumbling clothes is mechanically complex. Third is frequency control. If not perfectly tuned, high-power ultrasonics can generate audible screeching or heat up the transducers themselves. Despite these hurdles, the trajectory is clear. As material science improves and the cost of power electronics drops, acoustic desiccation is moving from the lab to the pilot plant. Startups are already working to commercialize the technology for industrial drying belts. We are standing on the precipice of a silent revolution. In the future, our laundry rooms will be cooler, our food more nutritious, and our deserts more livable, all thanks to the invisible, shivering power of sound. The water is there. We just need to know the right frequency to ask for it. Thanks for listening to G Fun Facts Online.